Hello there, and welcome back to Cosmic Whispers. Have you ever found yourself gazing up at the night sky, perhaps from a quiet backyard or a balcony in a sleeping city, and felt a profound sense of connection to those distant points of light? It's a timeless human experience, a silent conversation with the cosmos. Tonight, let us deepen that conversation by asking a truly unsettling question. What if the story of civilization, our story, isn't the first? What if, long before the first human cities rose from the soil of Mesopotamia, another world, a neighbor just across the void, had already lived through its own epic of rise and fall? Imagine a planet with sprawling oceans, winding rivers, and perhaps even beings who pondered their own existence under a soft crimson sky. That world is Mars. And if it ever hosted a civilization, then our entire timeline is not a beginning, but merely a chapter in a much older, vaster story. I invite you to hold on to that thought, to let it settle in as we journey together, because accepting its possibility changes everything we think we know about who we are and where we come from. For as long as human eyes have tracked the heavens, Mars has been an object of fascination and awe. Among the steady, twinkling stars, a few wanderers, the planets traced their own mysterious paths, but one of them was different. It glowed with a distinct, fiery hue, a deep ochre that seemed to pulse with a life of its own. It's close enough to be a familiar presence, a ruby dropped on the velvet cloth of night, yet it remained tantalizingly beyond our reach for all but the most recent moments of our history. That color, so reminiscent of embers and shed blood, has always whispered stories into the human soul. Ancient civilizations, seeking to make sense of the universe, projected their most powerful archetypes onto this celestial body. To the Babylonians, who meticulously charted the sky from their ziggurats, it was Nergal, their formidable god of war, plague, and the underworld. Its ominous glow was seen as a portent, a divine signal connected to the cycles of conflict and struggle on Earth. The Egyptians, too, saw its crimson face and named it Horus Dshr, or Horus the Red, associating it with their own pantheon of powerful deities. It was the Romans, however, whose interpretation would echo through the centuries. They saw in its bloody complexion the embodiment of their own god of war, Mars. This name, born of myth and fear, is the one we carry with us today. A linguistic fossil from an age when the sky was a canvas for gods and legends. But even as myths were woven around it, a deeper, more scientific curiosity was stirring. Mars never behaved quite like the other points of light. When the first telescopes were turned toward it in the 17th century, humanity saw for the first time that it was not just a wandering star, but a world. Observers like Christian Huygens sketched its surface, noting a large, dark feature that we now know as Syrtis Major Planum. He even watched it rotate, calculating the length of a Martian day to be remarkably similar to our own. Suddenly, Mars had a geography. It had days and nights. It started to feel less like a divine omen and more like a place. This feeling intensified dramatically in the late 19th century, a period of fervent astronomical discovery. It was an era when the line between rigorous science and romantic speculation could sometimes blur. The Italian astronomer Giovanni Schiaparelli, peering through his telescope at the Martian surface, described a network of linear features he called canali, an Italian word meaning channels, but when translated into English as canals, the word took on a life of its own. It ignited the public imagination with visions of immense, planet-spanning engineering projects. The idea was given fuel by Percival Lowell, an affluent American astronomer who founded his own observatory in Arizona, largely to study Mars. Lowell was utterly convinced that these canals were real, artificial waterways constructed by an intelligent, ancient civilization struggling to survive on a dying, desiccating planet. He drew elaborate maps, published books, and lectured widely, painting a vivid picture of a Martian society fighting against extinction by channeling water from the polar ice caps to irrigate their arid equatorial cities. Of course, we now know that Lowell's canals were an illusion. They were likely a combination of optical tricks, the human brain's tendency to see patterns in random data, and perhaps even the reflection of blood vessels in Lowell's own eye, pressed against the eyepiece during long hours of observation. The grand Martian civilization he envisioned did not exist, at least not in the way he described it. And yet, while the canals faded from scientific acceptance, the dream they represented never truly disappeared. The idea of Mars as a world that was once alive, a place that might still hold secrets of a lost past, became permanently lodged in our collective consciousness. With every new mission, every rover that touches down on its rusty soil, that old dream feels less like fiction and more like a tangible possibility we are on the verge of confirming. Today, our understanding of Mars is vastly more nuanced, built not on faint glimpses through a telescope, but on terabytes of data from orbiters, landers, and robotic explorers. We see it for what it truly is, a world of stunning, silent grandeur. It is a planet of superlatives, home to Olympus Mons, a shield volcano so vast it would cover the entire state of Arizona, its peak rising 3 times higher than Mount Everest. It boasts Valles Marineris, a canyon system that would stretch from New York to Los Angeles, dwarfing our own Grand Canyon into a mere scratch on the surface. We see its polar caps, majestic constructs of water and carbon dioxide ice that breathe with the seasons, expanding in the winter chill and shrinking under the faint warmth of the summer sun. Its surface is a silent museum, scarred and sculpted by a dynamic and violent history. We can read the stories etched into its landscape. The immense shield volcanoes speak of a time when its interior was molten and restless. The vast, smooth northern plains hint at cataclysmic floods or even a long-vanished ocean. And the countless craters tell of a brutal bombardment from space in the early days of the solar system. This is what makes Mars so utterly compelling. Unlike its sister planet, Venus, which hides its secrets beneath a suffocating blanket of toxic, high-pressure clouds, Mars wears its history on its face. It is an open book, inviting us to read the geologic chapters of its long and complex past. We can trace the ghostly outlines of dried riverbeds, watch colossal dust storms engulf the entire planet, and study the layered rock formations that testify to a world that changed over time, a world that once had a climate, a world that evolved. What draws us so inexorably to this cold, red dust ball is not just a scientific curiosity about its present state. It is a haunting, almost philosophical question about its past. Was it once like Earth? Did it ever host not just simple microbes, but perhaps something more? Could there have been forests, ecosystems, or even civilizations that rose and fell into oblivion billions of years ago? This is the core of Mars's allure. It is more than just a destination for our rockets. It is a mirror of possibility. It reflects a version of Earth that took a different path, a world where the conditions for life may have flickered into existence, only to be extinguished. It forces us to confront the profound question of whether life on Earth is a singular, miraculous accident, or if it is a common thread in the cosmic tapestry, a story that has already been told in its entirety on the world next door. And this brings us to the very heart of our investigation, where myth begins to yield to science. Was Mars ever truly Earth-like? When we picture Mars today, our minds conjure a landscape of profound desolation. We see an endless desert of red sand and rock under a pale butterscotch sky. The air is so thin, it's practically a vacuum. The winds are bone-chillingly cold, and the silence is absolute, broken only by the mechanical hum of our robotic emissaries. It appears to be the very definition of a dead world. But the most captivating story Mars has to tell is not about what it is, but about what it once was. The accumulated evidence, gathered over decades of painstaking observation, now points towards a staggering conclusion. Billions of years ago, Mars may have been a world we would have recognized. A world where liquid water, the essential solvent for life, flowed in abundance. A world with a thicker, warmer sky, where blue oceans may have washed against ancient shores. The story of this lost paradise begins with the scars left on the planet's surface. These are not ambiguous shapes or features open to wild interpretation. They are distinct, familiar geological patterns that have direct analogs here on Earth. Our orbiters, acting as our eyes in the Martian sky, have mapped countless dendritic valley networks, intricate systems of channels that branch and weave together like the roots of a tree. On our own planet, such patterns are the unmistakable signature of river systems, carved over millennia by flowing water draining from a landscape. We see great outflow channels, some hundreds of kilometers wide, that speak of catastrophic floods on a scale that beggars belief, torrents of water that once burst from underground and reshaped the surface in a geologic instant. And then there are the deltas. In places like Jezero Crater, the destination of NASA's Perseverance rover, we see the beautifully preserved, fan-shaped deposits of sediment that form when a river flows into a large, standing body of water, like a lake. The rover is there for a reason. A place like this, a tranquil ancient lake, fed by a persistent river, is precisely the kind of environment where, on Earth, the chemistry of life first sparked into existence. The very rocks and clays of this delta could hold, locked within their layers, the chemical fingerprints, the biosignatures of ancient Martian organisms. For any of this to be possible, Mars must have possessed a radically different climate in its distant past, during a period scientists call the Noachian epoch, roughly 4.1 to 3.7 billion years ago. Liquid water simply cannot exist for long on the Martian surface today. The atmospheric pressure is so low that it would rapidly boil away, even at freezing temperatures. Therefore, for rivers to flow and lakes to pool, Mars must have had a much denser atmosphere, one capable of trapping solar heat through a greenhouse effect and exerting enough pressure to keep water in its liquid state. A thicker atmosphere would have meant a warmer world, perhaps with average temperatures hovering above the freezing point of water in many regions. It would have meant clouds, rain, and perhaps even snow. It would have meant a water cycle, a dynamic system of evaporation, precipitation, and flow, just like the one that makes our own world a garden of life. The driving force behind this ancient, habitable climate was likely a planetary magnetic field. Much like Earth today, early Mars is thought to have had a molten convecting core that generated a powerful magnetic shield. This invisible force field would have enveloped the planet, deflecting the harsh solar wind, a constant stream of charged particles flowing from the sun. This protection was crucial. It acted as a guardian for the atmosphere, preventing the solar wind from stripping it away into the vacuum of space, atom by atom. But for reasons we are still trying to fully understand, the Martian dynamo eventually failed. The planet's core cooled and solidified, and its protective magnetic shield vanished. Without this shield, the sun's relentless radiation began to sandblast the atmosphere away. It wasn't a sudden cataclysm, but a slow, inexorable decline that played out over hundreds of millions of years. As the atmosphere thinned, the greenhouse effect weakened. The planet began to cool. The air pressure dropped, and the water on the surface began to boil off into space or freeze, retreating into the ground to become permafrost or migrating to the poles to be locked away as ice. What we see today is the geological ghost of that once living world, a planet frozen in time, preserving the memory of the rivers, lakes, and oceans that are now gone. This transformation of Mars from a potentially habitable world to a frozen desert is a profound cautionary tale. It shows that habitability is not necessarily a permanent state. A planet can be born with all the right ingredients for life, but cosmic misfortune can take them away. Yet the confirmation that Mars was once a water world fundamentally changes our perspective. It is no longer just a barren rock. It is a world with a past, a place that once possessed the same foundational conditions from which life arose on Earth. This elevates the question of life on Mars from the realm of idle speculation to one of urgent scientific inquiry. If the cradle of life was present, were any children ever born into it? The real mystery is not whether Mars could have supported life, but whether it actually did, and if so, what became of it. This line of questioning leads us deeper, from the evidence of rivers and lakes to the even more tantalizing possibility of vast, planet-shaping oceans. The evidence for rivers carving valleys and lakes filling craters is now widely accepted. But some scientists believe the story of water on Mars goes much further. They point to evidence of something far grander, an ancient ocean that may have once covered most of the planet's northern hemisphere. If this is true, then Mars wasn't just a world with scattered oases. It was, for a time, a true water world, a pale blue dot next to our own. This hypothesis is centered on a striking feature of Martian topography known as the global dichotomy. The planet is sharply divided into two distinct regions, the southern highlands, which are ancient, heavily cratered, and sit several kilometers higher in elevation, and the northern lowlands, which are much younger, smoother, and lie in a vast basin. This basin, known as the Borealis Basin, is so immense that it covers roughly 40% of the planet's surface. The theory posits that this enormous, low-lying region was once filled with liquid water, forming an ocean comparable in size to the Mediterranean Sea or even the Arctic Ocean on Earth. What is the evidence for such a breathtaking claim? Scientists have painstakingly analyzed data from orbiters like the Mars Global Surveyor and Mars Reconnaissance Orbiter, looking for telltale signs. One key piece of evidence comes from what appear to be ancient shorelines. Along the proposed boundaries of this ocean, researchers have identified geological features that look remarkably like coastal terraces, beaches, and deltas, all seemingly at a consistent elevation, just as you would expect for the edge of a massive, stable body of water. They have traced these potential coastlines, which they've named Arabia and Deuteronelis, for thousands of kilometers around the northern plains. Furthermore, the mineralogical data from the surface supports the idea of long-term interaction with water. The northern lowlands are rich in clays and sulfate salts. These are minerals that typically form on Earth in the presence of standing water over long periods. Rovers like Curiosity and Perseverance have also found layered sedimentary rocks, which are a classic sign of deposition in a lake or marine environment, where fine particles slowly settle out of the water column and build up over eons. Some of these layers even show evidence of recurring wetting and drying cycles, suggesting shorelines that advanced and retreated with ancient Martian tides or climatic shifts, creating the perfect tidal flat environments for the chemistry of life to begin. The case for a Martian ocean is not without its controversies, however. It remains a subject of vigorous scientific debate. Some researchers argue that the supposed shorelines are not at a perfectly consistent elevation and could have been formed by other geological processes, like volcanism or tectonic activity. They suggest that the vast northern plains may have been shaped by massive, short-lived floods rather than a long-standing ocean. Yet, as our data improves, the ocean hypothesis continues to gain traction. More recent studies have proposed that there may have been not one, but two major oceans in Martian history, separated by a period of intense volcanic activity that resurfaced the plains. The first ocean may have existed early on, with the second one forming after the massive Tharsis volcanic region rose up, deforming the planet's crust and creating a new basin for water to collect in. If Mars did indeed have an ocean, it would have had a profound impact on the planet's climate and its potential for life. A large body of water would act as a massive thermal reservoir, stabilizing the global climate and preventing extreme temperature swings. It would have driven a more robust water cycle, creating weather patterns, clouds, and rainfall across the planet. This environment, a world with climatic stability, driven by a vast ocean, with abundant energy from the sun and chemical nutrients from volcanic activity, is not just a world that could have supported life. It is a world that, by all accounts, seems overwhelmingly likely to have done so. The existence of an ocean would have provided an enormous, diverse, and stable incubator for life to emerge and evolve. This possibility forces us to expand our imagination. It shifts the question from was there life on Mars to what kind of life was there on Mars? Was it confined to microscopic extremophiles hiding in rocks? Or did the vast, sunlit waters of a northern ocean allow for the evolution of something more complex, something that could swim, grow, and perhaps even think? The loss of such a world is a tragedy of cosmic proportions. And it all comes back to a single critical event, the slow, silent death of the Martian atmosphere. A world with rivers, lakes, and even oceans cannot exist in a vacuum. It needs a sky. It requires a substantial atmosphere to provide the necessary surface pressure to keep water liquid and a blanket of greenhouse gases to maintain temperatures above freezing. Today, the Martian atmosphere is a ghost of what it must have been. It is incredibly thin, with a surface pressure less than 1% of Earth's. To stand on Mars without a spacesuit would be to experience near-instant death, as the fluids in your body would boil away in the low pressure. The atmosphere is composed almost entirely of carbon dioxide, with only trace amounts of nitrogen and argon. This thin veil is utterly incapable of retaining heat, leading to dramatic temperature fluctuations. While a summer day on the equator might reach a pleasant 20 degrees Celsius, 70 degrees Fahrenheit, the temperature plummets to a frigid minus 73 degrees Celsius, minus 100 degrees Fahrenheit on the very same night. This is no place for life, as we know it to thrive on the surface. So, where did the ancient thicker atmosphere go? The answer lies in the story of a planet that lost its shield. As we touched upon, early in its history, Mars almost certainly possessed a global magnetic field, generated by the churning of a liquid iron core, a process known as a planetary dynamo. This magnetic field would have been the planet's primary defense against the solar wind. For hundreds of millions of years, this invisible shield protected the atmosphere, allowing it to remain dense and warm, creating a habitable world beneath. But around 4 billion years ago, the Martian dynamo sputtered and died. The planet's small size meant it lost its internal heat much faster than Earth did. As the core cooled and solidified, the magnetic field collapsed. This was the pivotal moment in Martian history, a catastrophic turning point from which it would never recover. Without its magnetic armor, the planet was left defenseless against the relentless onslaught of the sun. The solar wind, a stream of high-energy particles traveling at 1,000,000 miles per hour, began to directly impact the upper atmosphere. This process, called atmospheric stripping, is like a cosmic sandblaster. Over eons, the solar wind particles collided with atmospheric gas molecules, knocking them one by one out into space, forever lost to the planet. We have direct evidence of this process still happening today. NASA's MAVEN, Mars Atmosphere and Volatile Evolution mission, which has been orbiting Mars since 2014, was specifically designed to study this phenomenon. MAVEN's instruments have tasted the upper atmosphere and have directly measured the rate at which gases are escaping into space. It has found that during solar storms, when the solar wind is particularly intense, the rate of atmospheric loss increases by a factor of 10 or more. While the trickle of gas escaping today is small, MAVEN's data allows us to extrapolate back in time. The conclusion is clear. Over billions of years, this steady erosion was more than capable of transforming Mars from a warm, wet world with a thick atmosphere into the cold, arid desert we see today. The decline was not instantaneous. It was a slow, creeping apocalypse. As the atmosphere thinned, the planet gradually cooled. The rivers faltered, flowing only intermittently before drying up completely. The lakes evaporated or froze over, their waters sublimating into the thinning air. The great northern ocean, if it existed, would have slowly receded, its water lost to space or locked into a vast subsurface layer of permafrost and polar ice. This story is a sobering reminder of planetary fragility. It demonstrates that the conditions for life are a delicate balance, dependent on factors deep within a planet's core. Earth has remained a habitable world because its internal heat engine has kept running, sustaining our protective magnetic field. Mars stands as a silent monument to what happens when that engine fails. Yet, even this tale of loss does not entirely close the book on Martian life. The disappearance of the surface water and atmosphere does not mean that all possibility of life vanished with it. Life is tenacious. On Earth, we find it in the most extreme environments imaginable, deep within the planet's crust, in subglacial lakes in Antarctica, and in hydrothermal vents on the dark ocean floor. If life ever gained a foothold on Mars, it might have followed the retreating water, migrating deep underground. Protected from the harsh surface radiation and the extreme cold, liquid water may still exist in subterranean aquifers, warmed by the planet's faint geothermal heat. Life, if it ever began, could be patiently waiting there, hidden in the dark, a final secret remnant of a world that once was. This leads us naturally to the ultimate question, the one that motivates our entire search. If Mars had the time, the air, and the water, did it also have that most precious and mysterious of phenomena, life itself? If Mars once gave rise to civilizations, they would have been creations of a world profoundly different from our own. To imagine them, we must first unlearn our earthly assumptions. The very elements that shaped our own history-abundant oxygen, vast oceans, and dense green forests would have been scarce or entirely absent on Mars. Their societies would have been forged in the crucible of a colder, thinner, and redder world, leading to cultures and technologies that might seem utterly alien to us. Consider one of the most fundamental forces in human development, fire. On Earth, the control of fire was a catalyst. It provided warmth, cooked food, kept predators at bay, and crucially, allowed for metallurgy. The Bronze Age and the Iron Age were born from flames hot enough to smelt ore from rock. But on Mars, even during its most habitable periods, the atmosphere was likely far less rich in oxygen. A fire there would not have roared. It would have flickered weakly, struggling for breath. This single constraint would have sent their technological evolution down a completely different path. Without powerful combustion, metallurgy as we know, it might have been impossible. Their mastery of materials would not have been forged in fire, but perhaps carved from stone, molded from native minerals, or grown from biological processes unique to their world. Their primary source of energy would not have come from burning wood or fossil fuels, but from the planet itself. Mars, a world of colossal ancient volcanoes, would have possessed immense geothermal potential. We can imagine their settlements clustered around these oases of planetary heat, drawing warmth and power directly from the ground. Their cities might have been subterranean, built into the warm rock surrounding geothermal vents, creating intricate, naturally heated complexes that offered shelter from the thin atmosphere and cosmic radiation above. They may have learned to tap into subsurface water sources, heated by the planet's core, creating sophisticated systems of irrigation and reservoirs that snaked through their underground communities. Their entire technological paradigm would have been geological, not chemical. Their great works would be feats of masonry, excavation, and hydrology, not of fire and steel. Their tools, their art, their architecture all would reflect a deep, intimate relationship with stone, ice, and the silent, patient geology of their planet. Culturally, a Martian civilization would have been profoundly shaped by the principle of scarcity. Survival on a world that was always on the edge of becoming uninhabitable would have demanded extraordinary cooperation, foresight, and resilience. Our own history is filled with empires that rose and fell on the bounty of fertile river valleys. Their history would have been one of careful stewardship of limited resources. Their societal structures might have been more communal, Their philosophies centered on balance and conservation rather than conquest and expansion. Even their perception of time would have been different. A Martian year, the time it takes for the planet to orbit the sun, is 687 Earth days, nearly twice as long as our own. Their seasons would stretch on for 6 long months at a time. This slower, grander rhythm would have deeply influenced their agriculture, their calendars, and their cultural cycles. Their myths and stories would not speak of a blue and green world, but of a vast, crimson landscape under a pale pink sky. Their gods, if they had them, would have been born of the desert, the wind, and the faint, distant sun. We can never know for certain what such a civilization might have looked like, but the act of imagining it is crucial. It frees us from the assumption that our way is the only way. A Martian society would not have been a mirror of our own. It would have been something entirely new, a testament to the creativity of life adapting to a world so like, and yet so unlike, our own. And this leads us to a deeper, more sobering question. If such a unique civilization ever existed, how would it have confronted the immense, existential challenge of living on a world that was slowly dying? If civilizations once took root in the red soil of Mars, their epic would not have been one of triumphant growth, but of a desperate, multi-generational struggle for survival. Mars is a far less forgiving world than Earth. Even during its most clement and Earth-like epochs, the planet would still have been a place of extremes, colder, drier, and subject to far more dramatic climatic shifts. Any society that emerged there would have had to embed resilience into the very fabric of its technology, culture, and architecture. Their greatest innovations would have been driven not by ambition, but by necessity. On Earth, nature's abundance was a catalyst for our industry. Dense forests provided the fuel for the fires that forged our metals, and a thick, oxygen-rich atmosphere made that burning process efficient. Mars offered no such luxuries. As we've considered, the thin air would have rendered large-scale metallurgy difficult, if not impossible. Their technological genius may have bypassed a metallic age altogether, developing advanced ceramics, stonework, and perhaps even biologically engineered materials that we can barely conceive of. Their structures might have been grown rather than built, using mineral-rich water to create crystal formations or manipulating native life forms to produce durable biological polymers. Stone and mineral resources would have been their bedrock, suggesting a Martian technology that was intimately connected to geology, a deep understanding of the planet's bones rather than a reliance on combustion. Energy, the lifeblood of any advanced society, would have posed another monumental challenge. Mars is further from the sun, receiving only about half the solar energy that Earth does. This faint sunlight would have been further diminished by the planet's infamous globe-spanning dust storms, which can block out the sky for months on end, plunging the surface into a dim, freezing twilight. A civilization reliant on solar power would have been incredibly vulnerable. They would have needed immense energy storage capabilities, or, more likely, they would have turned to more reliable sources. As we speculated, geothermal energy seems the most logical solution. The planet's history of colossal volcanic activity points to a once hot interior. Settlements built near these geothermal hotspots in the Tharsis region, for example, home to Olympus Mons, could have tapped into a near-limitless supply of heat and power. We can envision cities built not outwards, but downwards, following the veins of heat into the Martian crust. These subterranean sanctuaries would have provided warmth, stable energy, and protection from the lethal radiation that bathed the surface. Water, however, would have been the ultimate currency, the resource that dictated the location of every settlement and the focus of their most advanced technology. On Earth, our ancestors harnessed the power of rivers to turn mills and the predictability of rainfall to irrigate crops. On a drying Mars, the scarcity of liquid water would have been an existential threat. If civilizations persisted as the planet's climate changed, they would have become masters of water conservation. They may have engineered vast, underground aqueduct systems to capture and channel seasonal meltwater from the polar caps or from the slopes of volcanoes. They might have constructed colossal subterranean reservoirs, sealed to prevent evaporation, to store water for generations. It is even conceivable that they developed technologies to extract water vapor directly from the thin atmosphere, or to mine the subsurface permafrost, centuries before such ideas were ever considered on Earth. These systems would not have been mere public works projects. They would have been the sacred lifelines of their entire civilization. This focus on survival would have shaped everything. Transportation and communication would have been radically different. With lower gravity, moving heavy objects might have been physically easier, but the vast, empty deserts and thin air would have made long-distance travel perilous. Instead of sprawling interconnected empires like Rome or Persia, Martian civilizations may have been clusters of self-sufficient city-states, isolated in the few regions that remained habitable. Their technology would have been intensely practical, focused on adaptation and maintenance rather than expansion and conquest. This vision of a survival-focused Martian civilization helps explain why we have yet to find any obvious evidence of their existence. They may not have left behind the kinds of artifacts we are conditioned to look for. We search for the ruins of skyscrapers, but they might have built into the ground. We look for the rusted remains of machines, but they may have used stone tools of incredible sophistication or biodegradable materials that leave no trace. Their legacy might not be written in grand monuments, but in subtle, geological alterations that are nearly impossible to distinguish from natural formations after 1 billion years of silence. We might not even recognize the signs of their civilization if we were staring right at them. And that brings us to the next, most frustrating step in this exploration. If Mars once hosted entire societies, what kind of evidence could we possibly expect to find today? And why has it remained so stubbornly elusive? If a civilization ever etched its story onto the Martian landscape, even for a fleeting moment in geologic time, the question that inevitably follows is a simple one. Where are the ruins? On Earth, the past is buried just beneath our feet. We can trace the long arc of human history through the skeletal remains of ancient cities, the scattered shards of pottery, and the enigmatic tools left by our ancestors. It seems logical to expect that if Mars once harbored a civilization, we should find similar echoes of its existence. The reality, however, is vastly more complex, and the silence from Mars can be explained by 3 immense overlapping forces: the crushing weight of time, the deceptive vastness of scale, and the inherent bias of our own perspective. First, we must grapple with the almost unimaginable spans of time involved. The earliest civilizations on Earth, like those in Sumer or Egypt, are only about 5,000 to 6,000 years old. Yet even their most monumental structures, the pyramids and ziggurats, are heavily eroded, their lesser buildings reduced to dust and foundations. Now consider Mars, the period when it was most habitable. Its warm and wet Noachian epoch ended over 3.7 billion years ago. If a civilization rose and fell during that era, its remains have been subject to the slow, grinding forces of erosion for a period of time almost 700,000 times longer than the entire history of human civilization. Imagine a granite statue. On Earth, it might stand for millennia. On Mars, for billions of years, it would be subject to a relentless process of cosmic sandblasting. The planet's thin atmosphere offers little protection from the constant wind, which carries fine, abrasive dust that scours every exposed surface. Over millions of years, this process would wear down even the hardest stone, smoothing sharp edges, erasing intricate carvings, and eventually reducing any structure to a featureless mound. Add to this the thermal stress of extreme daily temperature swings, which would crack and shatter rock, and the constant bombardment of micrometeorites. Any materials we associate with civilization would, fabrics, even most metals would have disintegrated into their constituent elements eons ago. Time is the ultimate eraser, and on Mars, it has had a nearly infinite canvas on which to work. Second, we must appreciate the challenge of scale. Mars is an entire world. Its surface area is comparable to all of the continents on Earth combined. Our exploration of this vast planet, as comprehensive as it seems, has been incredibly limited. Our orbiters have mapped the surface in great detail, but even their highest resolution cameras can only resolve objects several feet across. A feature would have to be enormous and distinct to be identified as artificial from orbit. Our rovers, our robotic geologists on the ground, have performed miracles of exploration. But in over 2 decades of roving, their combined travel distance is less than 100 kilometers. Imagine trying to determine if civilization ever existed on Earth by landing a handful of remote-controlled cars in the Sahara, the Gobi, and the Australian outback. You would almost certainly conclude that the planet was lifeless and barren. The traces of a Martian civilization, if they exist, could be small, localized, and buried in one of the countless regions we have never seen up close. Finally, we are constrained by the limits of our own perspective. We are, by nature, looking for things that resemble our own history. We search for the geometric patterns of cities, the linear features of roads, or the monumental shapes of pyramids, because that is the signature we leave on a planet. But a Martian civilization, shaped by a different world, would have built differently. As we've considered, their structures might have been subterranean, carved into cliffsides like Petra, or blended organically with the landscape. Their ruins might now appear as chains of caves, unusually terraced hills, or peculiar geological depressions features that our automated mapping systems and even human eyes would likely classify as natural. We might have already seen the remains of a Martian city and dismissed it as a range of weathered mesas. This confluence of deep time, vast scale, and human bias makes the search for ruins an almost impossible task. Some researchers, however, point to a handful of strange and controversial anomalies in the Martian landscape geometric patterns, formations that uncannily resemble artificial structures, and of course, the single most famous and provocative image ever taken of Mars. While mainstream science largely regards these features as natural illusions, their story is a crucial part of this mystery. They force us to question the very difference between a natural landscape and an artificial ruin on a world where the lines have been blurred by billions of years of silence. When the first robotic eye sent back close-up images of the Martian surface, it was only natural for human eyes to search for the familiar. Our brains are magnificent pattern recognition machines, an evolutionary trait that helped our ancestors spot predators in the grass or find edible plants. But this strength is also a weakness. It makes us susceptible to seeing meaning where there is none, a psychological phenomenon known as pareidolia. We see faces in clouds, animals in rock formations, and as it would turn out, monuments on Mars. The most legendary example of this began with a single photograph taken in July of 1976. NASA's Viking 1 orbiter, circling the red planet, was snapping pictures of potential landing sites for its sister craft, Viking 2. As it passed over a region called Cydonia, it captured an image of a rocky mesa about 2 kilometers long. At that particular moment, the sun was low in the Martian sky, casting long, deep shadows across the landscape. When the image was beamed back to Earth, scientists at the Jet Propulsion Laboratory were stunned. The play of light and shadow on this particular mesa created an uncanny illusion. It looked unmistakably like a colossal humanoid face staring up into the void. It had what appeared to be 2 eyes, a nose, a mouth, and even a kind of headdress. The image was released to the public, initially dismissed by NASA as a simple trick of light and shadow, but it was too late. A face on Mars captured the global imagination like nothing before. To a public raised on science fiction and hungry for discovery, it seemed like the smoking gun irrefutable evidence of a lost Martian civilization. It was not just a random geometric shape. A face is a powerful symbol of intelligence, art, and identity. A torrent of books and speculative articles followed, proposing that the face was a monument, an effigy left by an ancient race. Some authors pointed to other nearby formations that they interpreted as a city and pyramids, suggesting the entire Cydonia region was a massive ceremonial complex, a Martian Giza. For over 2 decades, the debate raged. The single, low-resolution Viking image was analyzed and reanalyzed. Was it truly a monument, or was it simply a hill that happened to look like a face from one specific angle? Mainstream science remained deeply skeptical, but without better data, the mystery lingered. The answer finally came in 1998 and 2001 when the Mars Global Surveyor spacecraft flew over Cydonia, armed with a camera far more powerful than Viking's. It photographed the mesa several times, under different lighting conditions and in stunning high resolution. The new images were clear, detailed, and unambiguous. The illusion vanished. The features that looked like eyes, a nose, and a mouth resolved into a collection of ordinary pits, ridges, and slopes. The face on Mars was revealed to be nothing more than a heavily eroded, natural landform, a mesa shaped by billions of years of wind and geologic processes. The story of the face on Mars is a profound lesson in the power of human perception and the importance of scientific skepticism. Our minds are wired to find faces, and in the ambiguous shadows of a low-resolution photograph, our brains filled in the blanks and created a narrative. It was a classic case of pareidolia on a planetary scale. For most scientists, the case was closed. And yet, the fascination did not entirely fade. For those who believe in a lost Martian past, the new images were not the end of the story. Some argued that the formation was still artificial, just far more eroded than previously thought. Similar debates have sprung up around other images. A boulder that looks like a humanoid figure, rocks that appear to be arranged in geometric patterns, formations that resemble ruined walls. In virtually every case, closer inspection or alternative perspectives have revealed them to be natural geological features. The scientific community largely rejects these claims, not out of a refusal to believe, but because of a commitment to the rigorous standards of evidence. This tension is critical to understanding the search for life. A shape that looks unusual is not data. Science requires repeatable, testable observations that rule out all natural explanations. An extraordinary claim that a civilization existed on another world requires truly extraordinary evidence. A blurry photograph is not enough. Without physical samples, clear architectural features that defy natural formation, or some form of undeniable artifact, the idea of Martian ruins remains firmly in the realm of speculation. Science prefers to move slowly and deliberately, building its case on what can be confirmed beyond all reasonable doubt. And yet, this caution does not erase another, deeper truth. Even without intelligent builders, the Martian surface has been shaped by forces of immense power, forces that may have erased more than just rocks and hills. While slow, grinding erosion and the sheer passage of time are powerful enough to erase almost any trace of a past civilization, some researchers have proposed that Mars may have suffered a fate far more violent. They suggest that the planet's current desolate state is not just the result of a gradual decline, but was accelerated by catastrophic events, disasters so extreme they could have wiped entire ecosystems, and any civilizations within them, from the face of the planet in a geologic instant. One of the most controversial and compelling pieces of evidence fueling this hypothesis lies within the Martian atmosphere itself. Analysis of the atmospheric gases by our rovers and orbiters has revealed unusually high concentrations of certain noble gas isotopes, particularly xenon-129. On Earth, elevated levels of this specific isotope are considered a key signature of nuclear reactions, as it is a common byproduct of fission. To a small number of researchers operating outside the scientific mainstream, this atmospheric anomaly points to a startling conclusion. that Mars was the site of one or more massive thermonuclear explosions in its distant past. This theory takes several forms. Some speculate about natural nuclear reactors, rare geological phenomena where concentrated uranium deposits could have spontaneously initiated a chain reaction. Others propose a far more dramatic and unsettling explanation: the detonation of powerful nuclear weapons, the final act of a technologically advanced Martian civilization that destroyed itself through warfare. This idea, while captivating, is almost universally rejected by the broader scientific community. Mainstream science offers a much more prosaic explanation for the Xenon 129 anomaly. The process is known as cosmic ray spallation. For billions of years, the unprotected Martian surface and atmosphere have been bombarded by high-energy cosmic rays. These particles can strike the nuclei of atoms like barium and cesium in the soil, shattering them and creating a shower of secondary particles and isotopes, including Xenon 129. In this view, the isotopic signature is not evidence of a nuclear holocaust, but is the natural, cumulative result of eons of exposure to the harsh radiation of space. Still, the unusual chemistry keeps the debate simmering on the fringes of planetary science. Other geological features are sometimes cited to support the catastrophe hypothesis. Orbiters have identified vast regions of the Martian surface coated in a layer of glass-rich material, similar to trinitite, the glassy residue left behind by the first atomic bomb test in New Mexico. Once again, there are competing explanations. The mainstream view is that this glass was created by the immense heat and pressure of major asteroid impacts or by large-scale volcanic eruptions, both of which are known to have occurred frequently in Mars's history. The more speculative view connects these glass fields to the same hypothetical energy releases that skewed the atmospheric isotopes. Whether these catastrophic theories hold any water or not, they highlight an undeniable truth about Mars. Its history has not only been one of slow decay, but also of sudden, violent upheaval. We know the planet has been struck by asteroids large enough to trigger global climate change. The eruption of a single supervolcano like Olympus Mons would have belched enough dust and sulfur into the atmosphere to plunge the entire planet into a volcanic winter, killing any surface life. A civilization on Mars would have lived under a dual threat: the slow, creeping death of its atmosphere and the ever-present possibility of sudden, world-ending annihilation. Their history would have been shaped by disasters that make our own natural calamities seem trivial by comparison. And if that was their reality, then survival would not have just been about adapting to scarcity, but about enduring cataclysms. This brings us to the final, haunting chapter of their hypothetical story: the long, desperate struggle of a people fighting for survival on a world that was turning against them in every conceivable way. The slow, creeping death of their world would have become the central, unavoidable truth of their existence. Unlike on Earth, where life generally flourished in open spaces, expanding across continents and oceans, any advanced life on Mars would have found itself engaged in a long retreat. Their world would have been shrinking around them, the habitable zones contracting generation by generation, forcing them into ever smaller, more precarious refuges. This was not a struggle against a rival species or a temporary famine. It was a struggle against the planet itself, a battle they were destined to lose. We must not overlook the profound psychological impact of such a decline. If a Martian civilization possessed consciousness, art, and culture, it would have been a civilization defined by loss. Their entire worldview would have been shaped by the knowledge that their world was dying. Imagine their myths and legends passed down through millennia. They would not be creation stories of a world emerging from chaos, but perhaps sorrowful epics of a paradise lost. They would tell of a time when the sky was thicker, when great oceans stretched to the horizon, and when the land was not a uniform ochre desert. Their art might have been filled with imagery of water, their music with melancholic tones that echoed the whisper of the thinning air. Their philosophy would be one of resilience, certainly, but also one steeped in a deep planetary grief. Survival under such conditions would demand unimaginable creativity. Each generation would have been presented with a world slightly worse than the one before. They would have had to innovate constantly, not for progress, but simply to maintain the status quo. Their greatest engineering marvels might have been vast, subterranean shelters designed to seal in the last vestiges of a breathable atmosphere, or colossal atmospheric processors struggling to replenish the air that was bleeding into space. Their society would have been a testament to endurance, a culture fighting to hold back the inevitable night. But eventually, even the most resilient civilization would reach a breaking point. There would come a time when no amount of technological ingenuity could reverse the planet's fate. As the last pockets of liquid water froze or retreated deep underground, and the atmosphere thinned to a near vacuum, survival on Mars would have become impossible. Entire communities, the last bastions of a billion-year-old lineage, would have vanished, leaving behind only the faintest, most deeply buried traces of their long struggle. But what if, faced with the certainty of extinction, they conceived of one final desperate hope? What if, in their final days, they looked beyond their own dying world for a chance at continuation? For any species capable of astronomy, of charting the stars, the most obvious destination would have been a brilliant blue and white jewel hanging in their night sky. A world that was larger, warmer, volcanically active, and just beginning its own great story of life. That planet was Earth. If an intelligent civilization on Mars faced the final irreversible collapse of their biosphere, where could they have turned? Remaining in their underground shelters would have only postponed the inevitable. For a species that had mastered geology, energy, and survival, the most logical, albeit monumental, step would have been to look to the heavens. From the rust-colored surface of a dying Mars, Earth would have been a beacon. In their sky, it would have appeared as a magnificent evening and morning star, a vibrant point of light shimmering with the promise of vast oceans and a thick, protective atmosphere. To a people watching their own world fade to dust, Earth may have looked like salvation, a place where their species could find refuge, or at least where their legacy could be preserved. The idea of Martians physically traveling to Earth in great interstellar arcs is, of course, the stuff of classic science fiction. The technological hurdles would have been staggering, perhaps insurmountable, even for an advanced civilization. But we need not imagine fleets of spacecraft to consider the possibility of a transfer. There are other, more natural ways that life could have made the journey a process that is not only speculative, but is considered scientifically plausible. This theory is known as lithopanspermia, the transfer of life between planets via rock. We know for a fact that Mars and Earth have been exchanging material for billions of years. When a large asteroid or comet strikes a planet with sufficient force, the impact can be so powerful that it blasts chunks of the planetary crust into space with enough velocity to escape the world's gravity. These fragments then drift through the solar system as meteoroids. Over thousands or millions of years, the gravitational pull of other planets can alter their orbits, eventually causing some of them to cross paths with Earth and land on its surface as meteorites. This is not a theoretical process. Scientists have discovered and cataloged over 277 meteorites on Earth that have been definitively identified through their unique chemical and isotopic signatures as originating from Mars. Nature, it turns out, has been running its own interplanetary delivery service since the dawn of the solar system. The next question, then, is a profound one. Could life survive such a violent and arduous journey? The process would begin with a cataclysmic impact, subjecting any nearby organisms to immense shock and heat. Then would come a long voyage through the freezing vacuum of space, exposed to lethal cosmic radiation. Finally, a fiery plunge through Earth's atmosphere would subject the rock to extreme temperatures. It sounds like an impossible ordeal, and yet, surprisingly, experiments suggest that it is not. Microbes on Earth, known as extremophiles, have demonstrated an almost unbelievable capacity for survival. Some bacteria can enter a dormant, spore-like state, allowing them to withstand the vacuum of space and temperatures near absolute zero. Others have been found to survive radiation doses thousands of times greater than what would kill a human. The rock itself would provide crucial shielding. While the exterior of a meteorite would be superheated during atmospheric entry, its interior could remain cold, protecting any biological passengers tucked away in microscopic cracks and fissures. If this happened billions of years ago, when Mars was still habitable but beginning to decline, it could elegantly solve one of the great puzzles of our own planet as history: the surprisingly rapid appearance of life on Earth. Our world formed around 4.5 billion years ago, and for its first few hundred million years, it was a molten hellscape under a constant bombardment of asteroids. Yet fossil evidence suggests that by 3.5 billion years ago, life was already present and widespread. That is a remarkably short window for life to have emerged from non-living chemistry entirely from scratch. But if Mars, being smaller, cooled faster and became habitable earlier than Earth, life could have gotten its start there first. Then, as the solar system's violent youth continued, Martian rocks carrying the first living cells could have been blasted towards Earth, effectively seeding our young, fertile oceans with life that had already begun its evolutionary journey. This possibility reframes the entire relationship between our two worlds. They are not two isolated planets with entirely independent histories. Instead, they may be biologically connected, two successive homes for a single lineage of life. Life may have begun on Mars, and when conditions there soured, it found a second chance here. In this scenario, every living thing we see around us, the forests, the fish in the sea, the birds in the sky, and even ourselves might trace its ultimate ancestry back to a world that is now cold, silent, and red. This is the panspermia hypothesis, and it leads us to an idea so humbling and so unsettling that it could rewrite our entire understanding of who we are. If life on Earth was seeded by Mars, then we are in the most fundamental sense the Martians. The theory that life on Earth may have originated on Mars is a specific application of a broader, more profound scientific concept known as panspermia. At its core, panspermia proposes that life is not necessarily an isolated phenomenon, born anew on every habitable world. Instead, it suggests that the basic components of life, or even life itself in the form of hardy microorganisms, are common throughout the universe and can be transported from one world to another, riding on the cosmic currents of asteroids, comets, or interstellar dust. In this view, planets are not islands, but rather stepping stones in a vast, interconnected ecosystem. When we apply this lens to the early history of our solar system, the Mars-to-Earth scenario becomes a compelling narrative. As we've discussed, Mars likely had the necessary ingredients for life-liquid water, a protective atmosphere, and complex organic molecules long before Earth did. Our planet, being larger, took longer to cool down from its molten formation, and was subjected to more planet-sterilizing impacts for a longer period. There may have been a window of several 100 million years where Mars was a tranquil, water-rich world while Earth was still a violent and inhospitable place. This is more than enough time for the slow, patient chemistry of life to emerge. Imagine the scene on primordial Mars: shallow seas, warmed by geothermal heat, rich in dissolved minerals from volcanic rock. In this prebiotic soup, the first self-replicating molecules form, eventually leading to the first primitive cells. Life gains a foothold and begins to diversify. For millions of years, it thrives. But the solar system is still a cosmic shooting gallery. A massive asteroid strikes the planet, sending shockwaves across the globe and ejecting billions of tons of rock into space. Trapped within some of these rocks are colonies of Martian microbes, which are instantly thrown into a state of suspended animation by the cold vacuum. For millennia, These rocky arcs drift through space. Most are lost, crashing into the sun, being ejected from the solar system, or falling back onto Mars. But a tiny fraction, by pure chance, are captured by the gravity of a neighboring blue planet. They plummet through a young, oxygen-poor atmosphere, their outer layers burning away while their cores remain frozen. One of these meteorites lands in a warm, shallow sea on the primordial Earth. The rock cracks open, releasing its dormant passengers into a new world, one that is sterile but rich in all the nutrients they need. The Martian microbes awaken, begin to multiply, and the story of life starts its second chapter. The implications of this hypothesis are staggering. If panspermia from Mars is correct, then life is not a miracle unique to Earth. It is portable. It is resilient. It can survive the most extreme conditions imaginable and cross the vast, sterile emptiness of space. This would dramatically increase the odds of finding life elsewhere in the universe. If life can hop from one planet to another within a single solar system, it suggests that biology is a far more robust and widespread phenomenon than we have dared to imagine. But the most personal and profound implication is what it means for our own ancestry. If life on Earth was seeded by Mars, then our entire family tree, the very tree of life itself, has its roots not in the soil of this planet, but in the red dust of another. Every organism on Earth would be a descendant of that original Martian stock. Our deepest origins would not belong to Earth alone, but to a neighboring world that has long since lost its vitality. The idea is still a hypothesis, of course. Proving it would be incredibly difficult. The smoking gun would be to find life on Mars today, perhaps, dormant microbes deep underground, and discover that it shares a common biochemistry, or even a direct genetic link with life on Earth. If we were to find Martian DNA and discover it was fundamentally related to our own, it would be the single greatest discovery in the history of science. It would confirm that we are not alone, because our oldest ancestors are waiting for us, frozen in time, on the world next door. And this leads us to the most unsettling question of all. If we are Martians in origin, then Earth is not our beginning. It is only our continuation. What does that do to our sense of history, our identity, and our place in the cosmos? If we accept the possibility, even for a moment, that life on Earth was seeded by Mars, then our entire story, the story of humanity, does not truly begin here. It begins on another planet, under a pale red sky, in oceans that have long since evaporated into the thin air. In this telling, Earth is not the cradle of life. It is its second home, an ark that carried the precious cargo of biology forward after its original home became uninhabitable. This simple shift in perspective forces us to reconsider what it means to be human and what our place in the universe truly is. We typically tell the story of our origins as if it begins and ends on this planet. We speak of our earliest hominid ancestors, walking upright on the savannas of Africa, of the first villages forming along the fertile banks of the Tigris and Euphrates, and of civilizations slowly, painstakingly rising from the soil of this world alone. But if Mars is our ultimate origin, its celebrated history becomes only the most recent chapter of a much older, vaster epic. Humanity would not be simply a product of Earth's unique environment. We would be the latest, most complex expression of a biological lineage that began elsewhere. This alters our fundamental understanding of our own existence. Instead of life representing a singular, miraculous spark that occurred in Earth's primordial oceans, it becomes part of a larger continuity, a story of survival and migration. Our presence here would not be the result of a first genesis, but of a successful transplant. In this view, we are not the first beings in our solar system to ask questions, to build societies, or to gaze at the stars and wonder about our place within them. We may simply be the first on this planet to do so, while others, our distant biological cousins, may have already risen and fallen on a neighboring world, their history lost to the erosion of deep time. Such an idea dramatically shifts our place in the cosmic timeline. Human civilization is breathtakingly young, a mere few thousand years old. But if life on Mars had a billion-year head start, then the phenomenon of life itself, and perhaps even intelligence, may be far older than we realize. Our recorded history would cover only a tiny fraction of the complete story. The rest would be written in the rocks of another planet, an ancestral history erased long before we ever evolved the capacity to read it. It also profoundly changes how we think about our destiny. If we are the continuation of life from a dead world, then our survival on Earth is not a given. It is a precious and perhaps temporary reprieve. Life adapted to a new home and was given a second chance to flourish. This narrative frames our existence not as a story of dominion, but as one of resilience. It suggests that life itself is not fragile, but astonishingly enduring, capable of crossing the void and carrying itself forward, even in the face of planetary catastrophe. Humanity, then, would be both Earthling and Martian, biologically and historically bound to two worlds. This perspective does not diminish human history or achievement. On the contrary, it deepens it. Our beginnings would stretch back further than we ever dared to imagine, linking us to a cosmic story of loss, migration, and renewal. Our civilizations would not have risen in isolation, but would be part of a longer cycle. Earth's civilizations may not be the first in this solar system, nor will they likely be the last. This is why Mars matters so profoundly. Its silent, frozen history may hold the clues not just to its own past, but to the very deepest roots of ours. If we can one day confirm or disprove this ancient connection, we would not only understand Mars better, we would finally understand ourselves. And this brings the story full circle, back to the robotic explorers currently traversing the red dust, searching for answers. Their mission is not just planetary science. It is a quest to uncover our own origins. Every new mission that successfully touches down on the sands of Mars is more than just a triumph of engineering. It is a step back in time, a way for us to read the pages of a history that may be inextricably linked with our own. The rovers, landers, and orbiters that we send across the interplanetary gulf are not just searching for interesting rocks and signs of past water. They are searching for a lost chapter of our own story. They are our proxies in the greatest archaeological dig in human history. NASA's Perseverance rover, which landed in Jezero crater in 2021, embodies this new phase of exploration. Its landing site was chosen with painstaking care. Jezero crater was once home to a deep, tranquil lake, fed by a river that flowed down from the highlands, building up a magnificent fan-shaped delta. On Earth, river deltas are biological hotspots, places where fine sediment gently buries and preserves organic matter for billions of years. If life ever existed on Mars, a place like the Jezero Delta is one of the most promising places to find its fossilized remains. By drilling into these ancient mudstones, Perseverance is looking for biosignatures, subtle chemical, mineralogical, or structural patterns that could only have been left by living organisms. Even more crucial to this quest is the rover's secondary mission, to collect and cache the most promising samples for a future return to Earth. Perseverance is currently drilling core samples of Martian rock and soil and sealing them in ultra-clean titanium tubes. It is placing these tubes in strategic depots on the Martian surface, creating the first sample library from another world. The plan, a joint effort between NASA and the European Space Agency, is to launch a future series of missions to retrieve these sealed tubes and bring them home. The day those samples return to Earth will mark a pivotal moment. Here, in our most advanced laboratories, scientists will be able to analyze them with a suite of powerful instruments far too large and complex to send to Mars. They will search for the faintest traces of complex organic molecules, the microscopic imprints of fossilized cells, and the isotopic ratios that could finally tell us if life once breathed in the thin Martian air. Those samples could answer the ultimate questions. Did life ever exist on Mars? And if so, Is it related to us? Future missions will push the boundaries even further. They will venture into unexplored regions, searching for subsurface ice deposits or probing for liquid water aquifers that might still exist deep underground, warmed by the planet's faint geothermal heat. If life on Mars survived the Great Fading, it is in these hidden subterranean oases that we are most likely to find it. As we look further into the future, the very nature of our exploration will transform. With the advent of human explorers on Mars, the search will shift from robotic geology to hands-on archaeology. Robots are brilliant at analyzing what is directly in front of them, but human intuition, our innate ability to recognize subtle patterns, is uniquely suited for discovery. An experienced geologist or archaeologist on the ground could spot details a rover might miss: a peculiar alignment of rocks, a stratum of soil that looks out of place, a fossil fragment half buried in the dust. The first human settlements on Mars will not just be scientific outposts. They will be archaeological base camps from which we can begin to carefully uncover the secrets of a lost world. This next era of exploration will require a new mindset. We may need to treat Mars not just as a destination for colonization, but as a site of immense historical and perhaps biological heritage. Just as we protect ancient ruins on Earth, we may need to establish planetary parks on Mars to preserve its most significant sites. If life, even microbial, still clings to existence underground, we have a profound ethical responsibility to protect it from our own contamination. The future of Mars exploration, therefore, is a delicate balance between discovery and preservation. Whether we find the ruins of a civilization or just the fossilized remains of ancient bacteria, the discoveries will forever reshape our understanding of history, our origins, and our place in the universe. And so we arrive at the end of our journey, standing at the edge of a question that we cannot yet answer. The possibility of forgotten civilizations on Mars remains a tantalizing whisper from across the void, a story suspended in the space between scientific evidence and philosophical imagination. Yet, even without a definitive answer, the question itself has transformed our perspective. It has forced us to stretch our definition of history beyond the boundaries of our own world and to contemplate the profound idea that civilization may not be a unique terrestrial event, but a recurring chapter in the great cosmic story. Mars, in its current state of silent, frozen grandeur, holds up a mirror to humanity. What we see in that mirror depends on what future discoveries reveal, but either reflection offers a lesson of monumental importance. If we one day find incontrovertible evidence that Mars was once home to life, or even to a civilization, its story will become our prehistoric epic. Their ruins, however faint, and their fossils, however simple, will be the most profound discovery ever made. We would learn that we are not the first. Earth would no longer be the sole cradle of life, but the inheritor of a legacy, a second chance for a biological lineage that began on another world and was carried across space. Humanity would find its place in a much longer narrative, one of loss, survival, and cosmic continuity. We would be the descendants of a red sky, flourishing under a blue one. But if, after centuries of searching, we find nothing, no fossils, no artifacts, no biosignatures, only the sterile dust of a world that never was, then the lesson is just as powerful, though far more sobering. The silence from Mars would serve as a chilling warning. It would show us a world that had all the right ingredients for life, but through the slow loss of its atmosphere and the failure of its magnetic heart, saw its potential fade away. Mars would become the ghost of Earth, a vision of what our own world could become if its delicate habitability is not protected. Its silence would underscore the preciousness and perhaps the loneliness of our own existence, reminding us that a living world is an unspeakable treasure in the vast, indifferent cosmos. The true value of Mars, then, lies not just in the answers it may one day provide, but in the perspective it gives us now. The search for a lost Martian past is also a search for a deeper understanding of our own present and future. Each rover that lands, each sample that is analyzed, and each future mission that is planned deepens this story. Until that day of discovery, Mars will continue to hang in our night sky as a symbol of possibility. It is a mystery that may endure for generations, a cosmic whisper that invites us to look up and wonder. It reminds us that the universe is older, stranger, and more magnificent than our brief history suggests, and that the story of life may not be confined to a single world.